So I'm going to talk about some dynamics of training linear networks, shallow linear networks, which are in some sense one of the simplest models of neural networks, but that already have some interesting dynamics, which I think it could be key in understanding in general neural networks, which is some kind of balance between having some form of sparsity. In this case, it's a rank sparsity, so trying to learn linear maps that have low rank. But I think there's other types of sparsity depending on the type of the network. But this kind of balance where the network is biased towards finding these sparse solutions, but this bias towards sparse solution can also lead it to make it very hard to train, because it kind of the network will not want to. I like to call it the stickiness of, in this case, space of low rank matrices, where the network wants to remain low rank. And even though sometimes it may want to increase the rank, it will get stuck because of this stickiness in some sense. A bit fuzzy for the moment. It will be clearer later on. So this is joint work with two PhD students at Courant, Jem Feng and Santiago. And so what do I mean by lazy active? So it turns out that when you study limits of neural networks, when the number of neurons becomes very large, there's two regimes that have been identified, the lazy and active regime. The lazy regime is characterized by very fast convergence, because in the lazy regime, what you can do is some kind of linearization around the initialization, and so everything becomes linear, so you get very fast convergence. But because everything is linear, you don't get any kind of sparsity. And so even though the lazy regime is the one we understand the best, most of the interest now has moved on to trying to understand the active regime, because that's where we start to see some sparsity that kind of emerges from the training dynamics. And I would say we still have a very bad understanding of this active regime in general. In many cases, people just say, oh, we are not in there's ways to identify that you are not in the lazy regime. And so as long as you say that you are not in the lazy regime, then you know that you are in the active. But like there could be multiple active regimes, right? That's why one of the questions I'm interested in is there only these two regimes? Can we find other types of regimes? And also something that's been questioned is that it seems in practice that usually people are not, it seems that in practice we are not often in the lazy regime, but we still don't completely understand why is it so rare to be in this lazy regime. And what's kind of missing is some kind of phase diagram, let's say with number of data points, initialization, number of neurons, that will determine which regime you will be in. And that's something that we're definitely missing globally, but even in this simple model of linear networks, we're still missing this today. And that's one of the things that I'm happy to be able to answer with this recent result. And finally, it seems that a pretty important balance between these two regimes is that NTK has the advantage of having fast convergence but no sparsity. And the active regime starts to exhibit this kind of sparsity, which can be related to feature learning. And but at the same time, the same mechanism that makes this sparsity appear are the same ones that makes this model very hard to train and hard to guarantee that it will converge. And so can we get some kind of best of both worlds, getting both convergence or at least guarantees of convergence, and at the same time also sparsity, both at the same time. And the idea is that we will be able to get this, but you need some kind of mix of the two, a bit of lazy regime, a bit together that help each other. So, so all of these questions are still very open in general, and the fact that it's even in shallow linear networks, where it's one of the simplest kind of neural network model, the fact that we still cannot answer these questions means that it's important to try to it's a good first step to understand the general case. So what is a linear neural network? The intuition is that we want to learn a D by D matrix, so it could be any kind of task, right? It could be a classification task, but it's important to have multiple outputs because, as I mentioned, we're looking for low rank bias, right? So if you only have one output, there cannot be any low rank bias. So that's why we're looking only at matrix which have multiple outputs. In general, you could make it work without same input and output dimension, but it will make things simpler. And what we do is that instead of trying to learn this D by D matrix directly, A theta, which will be our D by D matrix, we represent it as the product of two matrices. And so a traditional neural network, there would be a non-linearity applied exactly in between of the two matrices. But if we remove it, that's what we get, right? Which is obviously kind of simpler. And what's called the width or is the inner dimension, the number of dimensions in the middle of the product, and we'll call it W for width. And in general, we take a random initialization, so all of the weights are initialized randomly. So it might seem kind of unconventional, right? Usually, if you were to just take a linear model, you wouldn't need a random initialization. But we'll see that actually this random initialization, so in general, it's used because if you initialize at 0, then the derivative, then the dynamics will just completely stop because there's a saddle at the origin. And so that's the reason why we do this, but we will see that actually by tuning this variance at initialization, it kind of allows you to move closer to the lazy or closer to the active regime and find the right balance in some sense. And yeah, so what we then do is that we train with gradient flow or gradient descent on a certain cost. The analysis will work for general cost C, which means that, yeah. So you see that since we have this product, right, the derivative of W1 is multiplied by W2. That's why if we were to initialize at 0, the dynamics would just completely stop. And that's why we need this random initialization. And I want to, even though most of the main results in some sense is general for any cost, we wanted to show that you could use this result to then prove in some specific problem to prove a phase diagram. And so the problem we're considering is the cost of trying to recover a certain low rank matrix A star, just observing A star plus some noise. And this is only possible if A star has some low rank structure. And the cost we're going to consider is that we try to fit so this should be A theta actually. So we're just trying to minimize, if you minimize this cost with A theta here, you will actually be able to recover under the right regime, you will be able to recover the approximate A star thanks to the low rank structure. And I would say it's kind of the simplest cost where you can see the advantage of low rank bias. That was the goal. Even though I don't know if it's something that's actually useful in practice. I don't know if that's a very common problem to have.
So do you pick W depending on the rank of A star or no?
No, that's one of the boundary. So I'm going to consider in general W to be in the overparameterized regime. So when W is larger than the dimension, so that you can represent any function. It's true that that's a completely, and we'll talk about this again. If you were to know the rank of A star, you could choose. You will then reconstrain the optimization. You could choose the width to be equal to the rank of A star. In this way, you can only represent function with the right rank. And you're kind of constrained towards finding the right solution. But then it's more the number of parameters that constrain you, or this width that constrains you. Whereas here I'm looking more at the dynamics, the fact that even though it could fit a completely bad solution, the dynamics will bias it towards the right one. Okay, so let's define these different types of dynamics. So in general, what we care about is really the evolution of A theta, not the weights themselves. And so we can just chain rule, and then we get the contribution of how the second weight matrix has changed and the first weight matrix has changed. And we see that basically if we want to understand the evolution of A theta, the two matrices we want to understand is this C1 and C2, this covariance of the weights. And at initialization, since these are random matrices, right, these are Wishart matrices, so you can just use Marchenko-Passau or whatever. In this case, actually, we'll focus on the case when the width is significantly larger than the dimension. So in this case, they just approach the identity, a scale version of the identity. And then you can actually look at the derivative of, say, C1. The derivative of C2 is similar. And you see that it has a similar formula, but now multiplied by A theta. And at initialization, A theta, so C is this product of V1 with V1, whereas A theta is the product of V2 with V1. Because of the fact that they are not correlated in some sense, A theta will be much smaller than C1 itself. And so in some sense, you can see that the derivative of C1 is negligible in comparison to the derivative of A theta. So in this kind of limit, as long as you assume for all time where A theta is significantly smaller than the size of C1 or C2, which is sigma squared W, you can as well assume that C1 are basically constant during training. So it's a bit this linearization I was talking about, that in some sense you can just leave it, everything remains as at initialization. And then we get some very simple self-consistent dynamics for A theta, right? Which is just, right, we see that it's it's basically just as if we were training a linear model directly, except we have this scalar factor in front, as just changing the learning rate, right? And so in this case, it's pretty obvious that it's a bit of a waste to have been using a linear network because we're just getting back to a deep linear, a linear network instead of just a linear model, because we're recovering a linear model, but we have even more parameters and so on, right? So I just want to mention that in the nonlinear case, this lazy regime is more interesting. So it's not just completely useless, but what's interesting in the linear case, it's really, this lazy regime is very boring in some sense. But, and obviously, right, we know how to prove convergence for linear models, so convergence is easy, but obviously we don't have any low rank bias, okay? And if you were to look back at the problem, I mentioned trying to recover this matrix, it would be easy to show that the loss will never approach 0 in this kind of lazy dynamics. So now the other types of dynamics that we understand that is well understood up to now is the so-called balanced dynamics. So linear networks have a very nice invariant, which is called balancedness. So we say that a network is balanced if the essentially outer product, so it's not the C1 and C2, right? It's the outer product in the other direction. So if these two outer products are equal, and the nice thing is that this is actually an invariant. If it's true at initialization, it will remain true throughout training. And so we can then talk about the balance dynamics, right? Because under the assumption, this will remain throughout training. And the nice thing is that from this, so already from this, we know that essentially W1 and W2 will have the same singular values. And the left singular vectors of W1 will be the same as the right singular vectors of W2. And actually, you can even extend this thing where actually all of both A theta, W1 and W2 all share some kind of common SVD decomposition, right? Where they share the same singular values, square root for the W and S for the other ones. And then again, the thing we want to understand is C1 and C2. We see that V1 must be equal to just this, which can be expressed in terms of A theta, square root of A theta transpose A theta. And we get, again, self-consistent dynamics, but are now quite different than the previous ones, right? We see that it's self-consistent dynamics, but the factor in front here depends on A theta itself. And one way that you can understand this is have some kind of momentum, multiplicative momentum effect, where essentially you will move very fast along direction where A theta is large and very slowly along direction where A theta is small, right? And it's easiest to see, this is even stronger to see when you look at the dynamics along just one singular value of A theta. The derivative of SI is going to be two times the derivative itself times essentially the gradient along this singular value, right? And so then it becomes very obvious that if there's one singular value which starts at 0, it will never become non-zero. So if you have a low-rank matrices, if you start with a low-rank matrices, you will never be able to increase the rank. And so that's the extreme case when you start with low rank, but there's kind of a stickiness in the sense that if you look at the space of low-rank matrices, if you're close to it at initialization, it will take you a very long time to escape this path. You will try the gradient descent will try to remain in the neighborhood of these low-rank matrices. And so yeah, that's why I took this stickiness. And the intuition is that this will help you, essentially if there's, let's say there were multiple solutions that could fit the data, and one of them is low rank. If you've started to being low rank, the network will prefer to go to this low rank solution because it can go there remaining in the neighborhood of this low rank set of function, rather than go to maybe the closer solution, which could be higher rank, right? So that's the origin of this low rank bias. And at the same time, so this stickiness, which is useful to achieve low rank bias, is also what makes proving convergence very hard, because if you need to understand dynamics well enough to guarantee that the SI will never come close to 0. And the thing is that you kind of want to start them close to 0, right? Because you want to start with a low rank and then slowly increase the rank. But so it's very difficult, and for this reason, I think there's a few results, but they need extremely strong assumption to prove that these balanced dynamics converge. Even though we get such a nice self-consistent dynamics, this is clearly not sufficient to actually prove any convergence guarantees. So before I move on to the result, I want to, so in general, yeah, we don't have very nice convergence guarantees for these balanced dynamics, but there's one specific case where things kind of decouple, and that's called diagonal dynamics. And these ones is one of the first type of dynamics that were understood for linear networks, but they are almost so simple that, and they need some very strong assumptions. So let's assume again that we are balanced, but now we further assume that A theta and the function you're trying to fit have the same, are all diagonals. You could also just assume that they all have the same singular vectors. Then it's the same up to, but let's assume that they are all diagonal, and also that W1 and W2 are diagonal. Then you can see that actually the dynamics completely decouple along the different diagonal entries, and so you just get a bunch of scalar dynamics, and you just need to solve them, each of them. And when you look at these dynamics, what's going to happen is that if you start from a small initialization, at first you don't move at all, and then very suddenly you start to fit at first, if you start from A theta close to 0, at first it will remain close to 0 for a long time, and then very suddenly converge to A star, right? And the intuition is that what you can do is that you start everything with a small initialization, and then at first, along the larger singular values of A star, you will have this very fast convergence, while the rest of the singular values have not yet converged, and then later on the other ones are going to converge. But if you stop early enough, then let's say if A star is rank k, if you stop after the first k large singular values have converged, then you can get a good approximation for A star. But you need to do this early stopping, stop right at the time when the first few have converged, but not yet the others. And so, yeah, this is some kind of incremental learning where, in some sense, you can think of it as first you try to fit the best rank 1 function, then the best rank 2, best rank 3, and so on, until converging to the last one. And so, yeah, these are very nice dynamics, and qualitatively, these dynamics match very closely what we observe in practice. But these assumptions are crazy. Like, it's not close to what people are doing in practice, right? You would need to, in some sense, to be able to take this thing, you would need to do an SVD of A star plus E at initialization. If you have the SVD, you don't need to do all of this, right? You can just learn the projection. So it's a very strong assumption. Okay, so what we showed is that we have these two self-consistent dynamics, but there's kind of a hole in the middle where we don't know what's happening. So either with this balanced dynamics or this very large initialization dynamics with this lazy initialization. And in some sense, there's a whole range of dynamics in the middle that we don't understand. And what we managed to show is that you can actually still get self-consistent dynamics in this middle regime. And then it will give us some dynamics that are englobe both lazy and balanced regime. So what we show is that these C1 and C2 matrices can be approximated in general by square root of A theta A, so that's the kind of balanced part, plus sigma 4, oh, that's a W2 actually, sigma 4 W2 times the identity. That's the lazy part, right? And so we see that it's kind of a sum of the two, right? So because what's important if we want to prove convergence is that this C1 doesn't become low rank, and so you have this kind of lazy part that makes sure that things don't become singular. And what's nice is that since we rely on some invariance of linear networks, you see that this approximation doesn't depend on time. It only depends on how wide on some, that's in some sense the variance at initialization. And that's related to how much wider the network is to the input and output dimension. But it doesn't depend on time.
So what's the dependence on T? You have C1 hat of T.
Oh.
There's no T on the right. Is it in theta of T?
In A theta.
Yeah, okay.
Yeah. Yes?
Sorry, on the last slide you were saying that gradient flow visits the projection for all k. So you're saying that it'll start at full rank and then it will just continue to decrease?
No, the opposite. So if you start from very small,
I see.
You start from approximating just a zero function and then just fitting the larger singular value, then just the two larger singular values and so on.
I see.
Yeah, and so we get these, what we call mixed dynamics in general, this general self-consistent evolution. And so obviously we see that we recover the pure lazy dynamics. So that's why I prefer to call pure lazy and pure balanced dynamics from now on. The case where the larger singular value of A theta is significantly smaller than this threshold sigma squared W. Because in this case, if A theta is significantly smaller than sigma squared W, then this term is completely negligible, and so you can just approximate it with the identity, and then you just recover the lazy dynamics. But if the smaller singular values of A theta is larger than the threshold, so all singular values are above the threshold, then you can completely forget about this identity term and you recover the balanced dynamics. But what's nice here is that we get all of the other dynamics in the middle, which are the ones where the mixed dynamics, where along some singular values you will have lazy dynamics, along the small singular values you will have lazy dynamics, whereas along the large singular values you end up with balanced dynamics. And so in practice, the way it's typically, the behavior is that at initialization, everything is lazy because we assume that that's roughly the size of the singular values at initialization, and they will be below this threshold. And then as you train the network, the singular values will start to grow. And depending on where the threshold is, some singular value might cross this threshold and then start to have this speed up effect coming from the balanced dynamics. And then these singular values that pass the threshold will converge very fast, while all of the other singular values that were below the threshold kind of remain stuck. And that's what allows you to have almost like a separation of time scale, where you can have very fast dynamics along the large singular values and very much slower ones along the other ones. And what's nice is that we get best of both worlds because we can guarantee we have positive definiteness for all times, right? Because we have this lower bound. Obviously, this lower bound can be quite small, so you kind of want to take this lower bound to be large enough to guarantee pretty fast convergence. But you still keep this kind of momentum effect for large singular values, which allows you to get this low rank bias. And yeah, and in some sense, I like to think of this as allowing you to tune how sticky you want this space of low rank matrices are, right? There's kind of an upper bound on how sticky it can be. You will never completely get stuck, right? It's impossible. The dynamics will never, as long as you haven't converged, you will still continue moving. You cannot get completely stuck as you could in the balanced regime. Let's show you a bit how it looks like. So again, on this task of fitting A star plus E. So here we plot the singular values through time, and we see that, so the black line is the threshold, sigma squared W. We see at first all singular values are below the threshold, and then the thing is that since it's trying to fit A star W, at first A theta will look like A star plus epsilon times a constant, right? But A star plus epsilon has k very large singular values and lots of small ones. And so these large singular values will be the first one to pass the threshold. Once they pass the threshold, you see this speed up effect, which makes them converge at a time where all of the small, this is the bulk of small singular values, have not yet converged. And so in some sense, if you stop training right at this time, you will be in the neighborhood of the projection to just the first k largest singular values. And so that's why we see in terms of the test error. So the test error is just the difference between A theta and A star. We see that the test error is minimized slightly, roughly at the same time when the large singular values have converged. And yeah. Oh, and also I guess we also show that the dotted lines are the self-consistent dynamics, where we can train directly on the self-consistent dynamics, or train a neural network, and we see a very good match between these two dynamics. So here first, maybe I should mention that the error is still pretty large, right? We just choose an example where we could still see the threshold nicely. Obviously, in general, you want to take an even smaller variance at initialization so that the threshold will be much lower and the speed up effect will be stronger. But this is more easy to, and then you can make this error go lower. So I can give you a sketch of proof. So as I said, it relies on some invariant. So in general, so I said that the balancedness was invariant. There's a more general invariant, which is the difference between these two outer products of weight matrices, which is an invariant value. And at initialization, since these are random matrices, but now these are random matrices where the inner dimension is very small in comparison to the outer dimension. And so these looks like random projections times sigma squared W. Two random projections which will be in general almost orthogonal, right? And since this is an invariant, we know that even though W1 transpose can change a lot during training, the difference will remain equal to this difference of projections, right? And then we get some kind of polynomial equation for the pair of matrices C1 and C2. On one hand, we multiply this invariant by W1 transpose on both sides. And since the invariant squared, since the projection squared will just be equal to the sum of the two projections, since they're orthogonal, and these projections are along the span of W1, we just get C1 back. So on one hand, we get this. On one hand, if you take the invariant squared again, you can solve for it and you get a big equation and another 3 equation for C1. Since this guy depends also on C2, you get the same equation for C2 and C1. So you get a pair of 2 degree 3 equations, which is kind of nasty, but somehow we can show that this C1 hat, C1 hat are at least one solution of this set of equation. Not the only one. Another obvious one would be C1 and C2 equal to 0, right? But you can then guarantee that you can rule out these other zeros and guarantee that since these two are approximately the same, you must be close to the right minimum. And yeah, so let me just check for time. Oh, I actually have time. So yeah, so let's now do a complete description of this low-rank matrix recovery, so that we can use this, the power of this approximation. So as I said, so we assume that we have A star has rank K star, and we have a noise matrix which has just random entries, and we do gradient descent on this mean square error cost. And what we want to see is what are the range of behavior you can get depending on how the different choice of variance sigma and width. So all possible variance and sigma as you increase how you scale the variance and width as a function of the dimension. And we want to get an idea of the behavior we get for all of these pairs. And so in this case, we just consider K star to remain fixed, right? So we have a very small rank matrices in dimension that grows. And there's a few constraints that we need to, so we want to get a phase diagram. There's kind of a few constraints that we rule out because they are kind of unreasonable. The first one, clearly, the second one a bit less, but I will talk about this later. The first thing is that you want to have a finite amount of noise at initialization. The entries of A theta at initialization should not blow up. And so for this, you can check that the variance of each of the entries is sigma 4W. So in general, we're going to assume that 2 gamma sigma squared plus gamma W is smaller than 0. So the variance actually goes to 0. And the other thing that I mentioned is that we need to assume for our analysis to work, we need the width to be significantly larger than the dimension. But which kind of makes sense because even though you could maybe, we don't assume that we know the rank K star in general. So in some sense, if you don't know the rank, you would need to take the width at least as large as the dimension so that you can make sure that you can fit any function. And it's then very easy to control when, so now we have this kind of 2 regime that we rule out, this kind of infinite noise regime, the underparameterized regime where the width is not large enough. And then we have this region of interesting initializations, interesting setups. And here we want to differentiate between these 2 regimes, the pure lazy regime and the mixed regime. So because there's actually no pure balance regime because you always start in the mixed, in the lazy regime. The signal will always start in the lazy regime, and they will become balanced after that, but there will always be some amount of laziness in the dynamics. But pure lazy regime would be the regime where all signal values, they start lazy and they remain lazy throughout the whole training time. And to guarantee this, since we know at the end the dynamics will end up at A star plus E, we need to guarantee, we just need to guarantee that at the end, the largest singular values of this guy is going to be below the threshold, right? So we just need to guarantee that the threshold is significantly above the largest singular value. And this can easily be guaranteed to be, this can be shown to be equivalent to this equation by just computation of size of these values. And so in this regime, everything remains lazy. So in this case, you can solve exactly the solution, what the dynamics are going to be. But basically, the intuition is that there's no separation of time scale. You don't learn the signal significantly before the noise. You just learn everything together. And so there's no time where you have just learned the signal but not yet the noise. And so because of this, you will never get, the error will never approach 0. And then you get the mixed regime if you don't have this, which means that if the threshold is below this value, it means that before the end of training, at least one singular value will need, at least the largest singular value of, since it will approach A star plus E at the end, at least one singular value will pass the threshold. Probably more, but at least one. And so this is what we call a mixed regime. And in this case, what happens is that we can control because the lazy dynamics at first are so easy to describe, we can describe pretty precisely at what time will the K largest singular value pass the threshold. And once this K largest singular value passes the threshold, we can switch to this balance dynamics. And the nice thing is that once they pass the threshold in a way that's actually already aligned in the same way as this diagonal setting I mentioned. So we do get decoupling, but to get this decoupling, we needed this lazy regime at first because the lazy regime is what allows the network the singular values to align themselves with the right singular values. So it's really, we see those two regimes helping each other because the short lazy period at the beginning of training allows for this alignment so that when you switch to balance dynamics, you're already aligned, you already have this diagonal dynamics, things decouple, and so we can get some very easy, we can really describe what's going on. And so then you can show that if you do early stopping, right at the time where the signal has been learned but not yet the noise, you can get a very small test error. So that was the intuition. Here is the more formal version. So if we assume that this assumption of being in the other parameterized regime, zero noise at initialization, then we get in the lazy regime, we can guarantee that for small enough learning rate, so that that the dynamics gradient descent is close to gradient flow, then we can show that the test error will never approach 0. And in the active regime, we can show that if you stop at just the right time, so delta kind of tells you how far away you're being from the transition between active and lazy. And so essentially, the further away you are away from the lazy regime, the longer you need to train, right? Because this delta, at the same time, right, this is the exponent, so it's just multiplicated with the exponent, so this is not a huge value typically. And so if you stop right at this time, then you can guarantee that the test error will go to 0 as the dimension grows to infinity. So it's not, you never reach true 0, only in the limit as the dimension goes to infinity. And even then, even if you were to just fit the low rank, it would not be possible. But and actually, if you look at this term, you can see that some of the terms here. So this error typically goes down as you get further and further away from the lazy regime. But at the same time, as you get further and further away from the lazy regime, you need to train longer there. So there's kind of a balance where you want to be at the right point between active and in this lazy regime to be kind of the right level of noise to guarantee good fast convergence. And so we can get these kind of phase diagrams where, so this black line is the infinite noise line. So everything above here, the black line is the transition between active and lazy. The red line is the infinite noise one, so we see that we get a very large error if we have in this kind of infinite noise. Even though in theory, at initialization, the error is infinite, but actually it does go down to 0 because it's still, in the end, it still converges to just A star plus E. But, and then we see that, essentially, as we get further away from this lazy active transition, we see that the error goes down. And so the further away we are from here, the smaller the test error. On the other hand, if we plot the training time, right, the number of steps we need to train, we see that the further away we are from the lazy regime, the longer we need to train. So there's this kind of trade-off. And finally, we can also plot, so this is the stable rank, so the ratio of the Frobenius norm squared divided by operator norm squared, which is kind of a smooth measure of rank. And we see that, yeah, this region is the region where we get, we recover the right rank, low rank solution. And anywhere in this kind of lazy regime, we recover a too large rank. And obviously, we also plot what happens for very small width. So normally our analysis only works for everything that happens above 1. But because we were interested in understanding also what has going on below, we plot also something there, and we see that it's only, so it seems that in some sense the behavior is kind of the same up to the actual threshold, the actual under-parameterized regime is closer to taking the width equal to the rank, not the dimension. Yes?
Is it correct that on the diagonals of these plots, the product sigma squared W is constant?
Yes. Wait. Yeah. These lines.
On the diagonals, right? The product sigma squared W is constant.
Yeah.
So your theory would predict that on the diagonal, the error should be roughly the same, right?
Yes.
So what's the explanation for do you have any idea what's happening towards the...
As you approach here?
Yes. Yeah.
So yeah, there's some other terms that depend on the variance at initialization. And that's basically this starting to happen. And so what's interesting there is that you see that if you had an initialization which is actually not exactly equal to the rank, but slightly larger than the true rank, you can even get good generalization even in this infinite noise regime. But I think this is a completely different dynamics because that's the constraint of having the right rank, of knowing the rank in advance. And so I think that's something quite different that starts to happen here, and that will require different. Yes?
I'm just sort of curious, in the middle plot where you're showing the number of iterations until minimal test error, are you holding the learning rate constant as you sweep across gamma sigma squared, for example?
No, we switch. So yeah, we need in general, in this mixed regime, you need to take a smaller learning rate.
I see. So you basically can analytically characterize what the maximal learning rate is, and you're taking that.
Yeah. But we don't do a sweep to try to get the best one. But so it's true that I would say that the number of times that is not quite final answer. It's just at the same time, right? This trade-off is actually not that strong because in some sense, right, this is just the exponent, right? The error is going to be d to the power delta, whereas the number of steps is just times delta, right? So it's not so much of a trade-off actually.
I see.
So that's why it's. And yeah. So yeah, I was pretty happy to be able to get these phase diagrams, something I was looking for a long time, and somehow it's now with this mixed dynamics, right? It's very easy to understand, to justify where the transition should be, which I'm very happy. And another thing which I was looking for is that one reason I felt it was so difficult to understand when this transition is that I always felt that this transition should be adaptive to the task. That maybe if the true task, if the true A star was sparse, you should be more likely the transition should be pushed higher, so you're more likely to be in the active regime. And if the data is not sparse, you will be more likely to be in the anti regime. And you do actually see this. So maybe first from this, right, we do see that the lazy regime is actually a very small region of the plane, at least of the plane with finite noise. So, and you see that the width that you need to start to be in the lazy regime needs to be at least 2, the exponent, right? So the width needs to be dimension squared to start to see the lazy regime, which is huge and not anywhere close to what people use in practice. On the other hand, but that's because A star was low rank. If A star was actually full rank, then the operator norm of A star, which will determine where the transition is much smaller. It's only of order square root of d, right? Because whereas before, when A star was low rank, then this size was of order d, which means that now the transition happens at 1/2 is equal to this instead of 1 is equal to this. So the whole transition has moved down. And what's nice is that it's really an adaptivity to the task, right? It's something that just from the true data, the transition changes. And so in some sense, the network adapts and recognizes that the task is not sparse, and so it's better to use the lazy regime in some sense, which is better adapted to non-sparse tasks. And if you have such a non-sparse task, then the crossing point, so the point where the start of the lazy regime appears, is only for gamma w is equal to 1. So in this case, you can get the lazy regime much earlier, right? And so I think that's probably one of the reasons why it's so difficult to track exactly where this transition is that to answer this question, you need to understand what the task is and to make assumption about the task you're looking for. And the final thing, which I already mentioned a bit, is that it was mostly because of our analysis that we assumed that the transition to underparameterized regime was when the width was equal to the dimension, but it seems that you can get some pretty similar dynamics even significantly below 1, right? At the same time, when you start to take a width which is below the dimension, you start to need to assume some kind of prior knowledge of the true rank, right? I mean, you could say, oh, I assume that it's constant, and so I can take width to be anything larger than a constant, which would still be fine. And it's not an extremely strong assumption, but it's already some level of assumption, right? If you really don't have no idea at all what's the rank of the true A star, then the only reasonable choice is to take the transition to be at above W. So yeah, so we get some very surprisingly simple and general self-consistent dynamics that kind of unifies these two directions of dynamics, this lazy and balanced dynamics that we were already well known, but we didn't really understand how they mix together. And we get best of both worlds. We get fast convergence thanks to lazy regime, to the early period of lazy regime at first, but we still get the advantage of sparsity. And one last thing, so the hope maybe there is also, I think this same question of you want some sparsity, but in some sense not too much, because if in nonlinear networks you can also have these problems where in this case it's like neurons clustering together and then it's difficult to push them apart and things like this. So this same kind of balance of you want sparsity, but you don't want too much, otherwise the network will start to have issues converging, is clearly there in the nonlinear case. I don't think we'll get anywhere close to as such a nice resolution for this balance in the nonlinear case, but hopefully some of these ideas could translate to the nonlinear case. Thank you.
Even in the linear case you presented here, so the loss you were using is like low rank plus noise. If you were to do like the standard matrix completion type of loss, where you just zero out entries, do you still get?
So we were working on this. So first of all, the proof, actually, at first I was expecting that once we have this first theorem, proving the rest would be quite easy, because thanks to, in some sense, things should almost decouple directly. But it turns out that it doesn't, it almost decouples and so on, so there's lots of approximation to propagate. And the problem is that because of this separation of time scales, it's difficult to do a Grunwald type argument, because you will have along the Lausinger values, things are very unstable. But at the same time, you converge very fast, so then the dynamics kind of stop along these directions while not along the others. So our goal was to do the matrix completion case, but then we realized that there's some, but it should definitely work. I mean, we were pretty close, but it's a matter of probably. I think what we need to do is just find. Basically, in the end, we had to do the Grunwald by hand, almost like showing up to now, looking along the different signal values and. Do a much more complex type of Grunwald. Probably if we find a way to simplify this, then the matrix completion should come much easier. But,
Do you have a sense of what would happen if you tried deeper linear networks?
Yeah, that's so it feels almost like you could just use this because a deep network is made of smaller, shallow networks, right? So and if you were to do this, I think you could get some interesting result. But So we know in the deeper case, we already know what the pure balanced and pure lazy dynamics are. And what's going to happen in the balanced case is that instead of having a square root here, first of all, we get more terms, a few more terms, but in some sense, this exponent is going to be depth minus, some exponents that instead of being 1/2 will approach 1, right? So a higher power. But somehow just changing from this power 1/2 to slightly higher actually completely changes the rate, because essentially when you leave, so the speed up effect is kind of exponential as you start to have this momentum effect. But once the exponent is larger, the speed up becomes like 1 over the time, right? So there's a finite time explosion. So the whole dynamics change a lot. But I'm quite confident that you could get probably something like this, where also kind of a mix of the two. At least empirically, that's what we seem to observe. It's just that I'm not sure if the exact same proof technique would work. Maybe, so we like this proof technique because it works for any time. But you could there's actually another way to prove the same thing, where you can do a more Grunwald type argument. And so maybe this would have more chance to translate to the deep case. But I'm sure there should be some kind of formula for the deep case. At least I have pretty good hope. But, yeah.
All right, thank you.